Good morning. My name is FlorianTang, and I will present the new developments in ChemApp for Python that have been added to recent versions of ChemApp. In this talk, I will go through this Jupyter notebook, not to a presentation, so that I can directly work with the code, because I feel that the simplicity that the ChemApp for Python interface offers is best illustrated in this type of way. So we will go through the introduction part, which is very small, and I say there's nothing really new here, but I still think that is worth an introduction for those that haven't heard about ChemApp for Python yet, so that you can follow along, as well as the then following deeper look into how we can work with stream objects and how we can work with process modeling tools that have been added to ChemApp for Python in the recent version. And then I will follow up with some tiny helpful additions that I feel worth communicating have been added to ChemApp for Python. So fundamentally in this script, the beginning is probably always the same, or almost the same in every ChemApp for Python calculation script. We do import some packages that we don't really that we're just using as tools. And then from ChemApp, we are importing, and this is a bit of a convention of mine, which I try to communicate throughout the documentation as well, that we do call ChemApp CA, and that we do have abbreviations for stream calculation, which is CASC for the thermochemical system, which is CATS, and the standard equilibrium calculation, which is CAEC. The other things we are importing here will be talked about later on by me. This is also just convenience functionality from the ChemApp package. So naturally, in doing so, we will start by loading a data file. This data file I created from one of the commercial databases of FactSage, so it is a CST file, and it is as simple as defining the path. It could also just be the string, and then just loading the data file. Now everything is loaded in the back end, the ChemApp DLL is loaded, and everything of the thermodynamic system is there. Since we do not have a GUI for ChemApp for Python, it may be worth to investigate what has been loaded. There are some convenience functions here, which I can just briefly show. So one of them is that we do have the getCSTInfo string, which is more or less every meta information that is saved in the CST file. Particularly relevant is the expiration timestamp. Every CST file has an expiration timestamp that is coupled to your license, I think. It does have a allowed user ID that is allowed to open these files. For me, this is the developer's user ID of ChemApp. For you, it would be your specific one. And then the other information may be worth keeping around for debugging or information purposes. This was about the file, so now we can also look at the thermodynamic system. There are a few functions that provide this information. I will just go through these. So one of them is getString for the SC, which is system components, and then it's plural, so it means for every system components. And you can just get a list of these system components. It's in itself obviously not super helpful, and I kind of hinted at this by giving the file name with all the components, but this is the elemental system components, and the fifth one is the actual electron that is needed for the spinel phase. Similarly, you can look at the phases and the phase constituents. This is a rather expensive list of all the gas species that are in this data file. I did select every gas species for the selected elements, so there's probably quite a few not so relevant for the type of calculations that we want to execute, or probably all calculations ever. However, this is the contents, and this is even larger than the allowed window size for this one, so I will go through this too. So with phase index 1, there is the slag liquid, which is included, which has the FeO and Fe2O3 constituents, and so on. And in the end, there are all these compounds that are part of the data file. So this is already a pretty good and worthwhile information to have about the CST file, because sometimes you will not remember, or you very likely will not remember, either the index number or the exact name of such a phase and how it is abbreviated into a CST file. After having done this, I do have a very bogus example calculation that I will just briefly go through. So one of them is that we're setting that we're using methane and hydrogen to reduce iron oxide. I'm putting a not really here because all these process parameters and the amounts are totally made up. So it's just an artificial calculation. We start with just a best practice to set the units in the beginning, and then I will do a stream calculation. Just this is because I want to have the higher complexity of a stream calculation that introduces different temperatures of incoming species and so on. So for this one, this is the actual equilibrium calculation, which would be the reactor itself probably. So I just set arbitrary temperatures of 110, 1100 at Celsius, as I set it above here, and then the pressure to be 1 bar. This is very close to the defaults anyways, but I'm just doing this explicitly. Now for the streams, I did come up with a scenario that we do have a separate parts of the reactor being fed into, which is the iron oxide inside the reactor that is going to be at 750 C and standard pressure. I will have an atmosphere that will contain the oxygen-nitrogen mix that takes part in the calculation. At 500 C, I will have a methane input at 100 C for some reason, and the hydrogen will be at room temperature. This is now setting up 4 streams with these 4 names and these 4 properties, similar to how you would do on the Equilib first page. But now you are also not only giving numbers for these streams, but you can also give names for these streams. Now, we do need to fill these streams with some content, and I picked these constituents. So for the iron oxide, we're just using pure hematite, and this is how we can input the stream constituents. So to this stream, we will enter this phase and this constituent. You are not obliged to do this since this is a compound. You could just as well just remove this, but for me, it's just the clarity of being that the phase constituent of a compound is the phase itself. I just always do it like this. We do add some amounts. This is going to be kept constant throughout the calculations, so we're just doing this once. And now we going to the variable inputs, and the variable inputs in this case are going to be the methane content and the H2. And for the stoichiometry of the reaction, I just came up with 1 minus A for CH4, and H2 is 3 times. This is obviously just as arbitrary as anything in this example, and we're just going from 0 to 1 in steps of 0.02. So for those that have been using NumPy, this is one of the convenience functions of NumPy that I use all the time. Also, it's just very easy. So we're setting up the range very similar to how it is done in Equilib 2, where you would type just 0, 1, and 0.02. But in this case, we also need to increase the upper limit by just the step size once to include 1.0. There's obviously nothing wrong with this function. It's just a different convention. And we do set up a results dictionary so that we can keep the results after the calculation. I would just execute these cells, and now we can go into the meat of the calculation, which is where we are iterating over this range for the variable A, and we're setting the content of methane and hydrogen respectively, just as we drew it up previously. And now the only thing which is also noted here that I want to point out is that after we do the calculate equilibrium, we are explicitly getting the result object of this calculation. This is a very crucial element for everything that follows behind this part of the calculation, because otherwise, while iterating, we would only calculate but do not fetch these results automatically. So this has to be done like by this routine, and this routine will fetch, I think, almost every usable thermodynamic property that can be collected from an equilibrium calculation. You can also see that I wrap this routinely into a try except block where I'm fetching ChemApp errors. The ChemApp errors do come with the error number, which may be informative about what's been going on, and depending on how you set your calculations, there may be conditions where you cannot calculate a solution, which will raise this type of error. And since we do not want to interrupt the iteration over all the A variables, we are going to use this try except block and then just store away these errors or just print an error message. However, in our example here, everything should just work fine. And now we do have these this results dictionary where for each value of A, we do have a respective result object. So in this post-processing, I would just go very briefly over this. I'm using some other libraries to just elevate the overall mechanism. And I could show you the script, but I don't want to go into details. I would just plot the delta H with this T, which is like the exothermal reaction, kind of depends on A, which is expected. I maybe have not expected that this would be such a straight line, but it is apparently such a straight line. And now, again, just a brief reminder, we can fetch these names of the phases from the thermodynamic system, or we can just remember the name. I would just print all the phase names here. So if we're interested in the results of a specific phase, this is just a good reminder that you can pick this name from right around here. I will do another two tiny plots that are informative about what's been going on throughout the calculation. So this is the phase amount over the variable A, and as you can see, the gas phase amount is more or less constant throughout the iteration of A, which is likely because I just set up the ratios of methane and hydrogen respectively, but we do have a switch where the iron is actually higher at low A and then decreases with increasing A, and the monoxide is increasing subsequently. The same, or maybe not the same, but now we are going to look at the phase constituents of the gas phase, because obviously, even though I did obey the same stoichiometry, not the same stoichiometry, the total amount to be more or less constant. If you look at the different phase constituents of the gas species, plotting over A again, you can see that there's quite different trajectories for these. This is just to inform that there's like some changes in the data. Now the interesting part starts now. So now we are going to work with these stream objects. The logic behind having to work with stream objects is that the ChemApp library itself is a Fortran library, which is really just a sequential procedural program that runs. So you need to make your inputs, you press calculate, and afterwards you can fetch your results. And this is always very procedural. So you need to start somewhere and you need to end somewhere, and there's no going back as easily. So we're just keeping all the results of each calculation. We need to associate, obviously, where we come from. So we use this results dictionary. And now we're just looking at this value of A, which was 0.1 in this case, is just an arbitrary selection. And to start with how this can be investigated is that we can print these results objects. And if you look at this results object, this is now ChemApp for Python. This is not entirely ChemApp anymore. There's some meta information about the calculation itself. Then it does give you the output of how the calculation input was presented by ChemApp. So obviously we do have the different streams here. We do have the stream numbers, the different conditions of the streams, and this is the content. And now this is the actual calculation results. This is quite expensive. Again, so there is a lot of data about each phase, even though these are not stable. All the activities and the chemical potentials are calculated and stored, and in cases of stable phases, for example, this is for the gas phase, all species do carry their respective results for all the thermochemical properties that can be fetched for them. This is quite a big data set, and this is present for each value of A. There's also like these the system split by system components and all this. So now the magic can happen when I use the routine, which is like create a stream from this results object. So in process calculations, obviously chaining different types of calculations and following up on each calculation with a modification of the result, and then, for example, iterating on these is crucial. And in this case, we can just use the create stream. And when I do this, I will just print the result as a stream. And now you do get a stream state class. I'm just printing the result. The class is obviously a Python object that will be the stream that has the conditions set up as like the reactor was set up, and then all the amounts of each phase constituent that is in this system is part of this stream state. The zero amount phase constituents obviously aren't part of this, but every other is. These can now be directly used to be fed into the next calculation by using the .set st, which is the set stream routine of a stream calculation, which just takes this object and can basically put all of this information as a new input stream into the next calculation. This is how you would reuse these stream objects. However, these functionalities were present in ChemApp for Python previously too, and now the new things that have been added recently are coming. So one thing that was requested by customers is that the create stream routine should have the ability to include, exclude, or modify what is actually carried over into these stream objects. So we did implement this in such a way that now you can, for example, exclude certain phases. In this case, we're just excluding the gas phase, and suddenly the stream will only contain the monoxide constituents of FeO and Fe2O3, and then even some tiny amount of pure FCC iron. This is now without the gas phase. Obviously, all these different species that are stable but in very small amounts have been somewhat obscuring the perspective towards this stream previously. So now we can also have different exclusions. Now this is going to be the element exclusion. So in this trigger, you can use, you can ignore all the constituents that do contain iron. For this, we need to provide the phase config that we do know which of the phase constituents do contain iron. And if I do that, you can get this more or less, I'm not sure useless, but this is a very strange view of the results, because now it's only the species that do not contain iron. And this one, there is exactly the 3.5 mole of non-iron system components. Again, now we can exclude, for example, as an example, just to illustrate this, oxygen, but also set up a threshold. As you can see in this previous overview, there's quite a few gas species that have very small and quite irrelevant amounts. So now if we just set the element threshold to 1e minus 10, you can see that it's now only including those that have higher concentration of that. We can also have different exclusions. Now this is going to be the element exclusion. So in this trigger, you can use, you can ignore all the constituents that do contain iron. For this, we need to provide the phase config that we do know which of the phase constituents do contain iron. And if I do that, you can get this more or less, I'm not sure useless, but this is a very strange view of the results, because now it's only the species that do not contain iron. And this one, there is exactly the 3.5 mole of non-iron system components. Again, now we can exclude, for example, as an example, just to illustrate this, oxygen, but also set up a threshold. As you can see in this previous overview, there's quite a few gas species that have very small and quite irrelevant amounts. So now if we just set the element threshold to 1e minus 10, you can see that it's now only including those that have higher concentration of that element. There are, as you can see, like this, for example, there is a species that does contain that the total amount is less, but the oxygen amount in this is the next part of this presentation will be about the possibility to split streams by matter of state. And in this case, we're just creating the stream again. I'll just start new, so because of the modification we made previously. And now I can split by states. We do have the ability to determine the matter of state of a phase in ChemApp for Python, and by doing so, we will receive 3 different stream objects that are split. I will just briefly show this. So the solids obviously do not contain the gas phase, and therefore this is the total amount. And then the liquid, sadly, no liquid stabilized ever in this calculation, so there is a stream that doesn't have any constituent in there. I could also obviously show the gas constituent stream, but that is also shown above. We can also, now going back to the gases of this reaction, we can also say that we want to purge all those that are below a certain threshold. So we do want to remove some. This is a new functionality too, so that you can, for example, remove from gas ID all those very low amounts of complicated phase constituents, maybe to just get an easier view. And as you can see, by removing all those that are below 1e-5, we didn't even change the total amount at all, so these are fairly insignificant in general. This is obviously mostly for convenience and for making the data more manageable. In the solid streams, we can also use this create solid stream, so not only split a stream into the three different matter of state that we had previously, but we can also directly create the solid stream and also obviously create the gas and liquid stream. This will yield similar to the one that excludes the gas phase, this one. This is mostly because this is such a limited example. We can also combine stream state objects after we created them. So now we are going to combine only the solid phase, which is the previous object we created here, with only the relevant gas phases, gas phase constituent, and by doing so, we do get a somewhat tidy version of what we had previously, but where we are simply looking at those that have relevant amounts. It is free, well, not free, but it's fairly straightforward in typical Python way of doing things that you can just manipulate certain properties, and therefore the solid phases are. For example, like this stream will just be set to have a temperature of 2000 C now. This can be done with a pressure, with temperature, and also with some other properties. For example, the name could also just be modified like this. In the splitting, we can also split just by state a certain stream. This has been done previously, but just to briefly show this, we can also split at a certain threshold of values. So you can say we want to have all the tiny ones or only the big ones. I guess this is the more often used situation. And then also the remove above threshold and you remove below threshold functionality will just get rid of some of these constituents. At the very end, I want to show these other helpful additions. What we have added is a composition class, which is very closely modeled after the PyMatGen composition class. If anyone is using PyMatGen, they will feel right at home. This allows to do some parsing and understanding of chemical formula, which is very frequently occurring in the type of user requests I do get for ChemApp for Python, how this can be done. And as you can see, you can, for this type of formula input, you can get quite a few different ways to normalize or look at these. You can get the elements, you can get the dictionary of these, and you can get, for example, a number of atoms. This is all very helpful information when you are doing calculations, for example, for total stoichiometries and all of this. This isn't limited to such compositions. It can also be done for these rather complicated ones, because it's relatively powerful in the way it can parse this. Along with this functionality, the maybe a bit more obscure switch components has been introduced, which is also very helpful, and I hope to explain this nicely enough. So in the switch components routine, you are able to find to basically find a new way of expressing a composition stoichiometry with a list of those components you want to use to do this. This is quite helpful if you are, for example, like in this below example, if you are looking to express a certain salt into different system components, or in oxide systems where you have system components that aren't pure elements, you can see that this composition is, for example, made up of 2 NaCl and 1 SrCl2 mole. This is a very helpful routine if you need to recalculate compositions to work with this system component input for ChemApp, for example. There is some features that come with switch components. One of them is that you can give a tolerance. This is very helpful if, for example, in ASH calculations, there's some red analysis of complicated compositions that can be like off stoichiometric, and this would raise an error if we wouldn't be allowed to lower the tolerance to express this in these system components, but in this way we can get a good enough result by setting the tolerance to 1e minus 2. And along with this, the logic to be able to give fractional molar amounts is just a very, I think, very consequential thing. So in this case, you could just normalize that the total size of this vector is normalized to 1. The last addition that is basically the, just like as an apple shows, the one more thing is the recent addition that allows much easier input of complex formula. And to show this, there is now a new method, setIA-CFS, which stands for complex formulas. And this allows to just list all the chemical formula you want to input into our ChemApp calculation, and then the amounts associated with these, and this will set up the calculation in such a way as in, I guess you can get that these are the total amounts of the system constituents, the system components, that this is calculated for all of these. This is very close to how equilib output works or input works, and obviously this would also work if I wasn't using mole or were using any arbitrary unit. And obviously, after doing this type of setup, you can just get started by calculating and fetching a stream state object. Thank you very much, and I hope to have piqued your interest for the stream calculations and the new additions in ChemApp for Python. This example will likely end up in a slightly modified way on the website. Thank you very much, and I'm waiting for your questions.